What you notice on this side is this is what we're going to call logarithm form. That's a logarithm. It's pretty straightforward because it has the word log right in it. That's a logarithm. And on this side over here, that's going to be our exponential form. And I hope you recognize it's exponential because it's got an exponent up there, right? And there is no word log, so log does not exist in here. But these two things, this logarithm can be rewritten as an exponential and vice versa, okay? You see their example there, but let's just go ahead and work on this and let's try to change it, okay? If I were going to read this out loud, log 416 equals 2, if I'm going to read that out loud, it reads like this. It reads the logarithm base 4 of 16 equals 2. That's how I would read this. The logarithm base 4 of 16 equals 2. Now it uses the word base. Now think about this. If we can write a logarithm as an exponent, does an exponent have a base? Yes, it does. So obviously my base is right here. The 4 is called the base. And what does the base look like if you were going to write something as an exponent?
4.
Yeah, it's the big number. It's what you're raising your power to, right? So this is 4.
To the 16.
Okay. Now, the answer to a logarithm is an exponent. So this is going to be an exponent.
Oh, so 4.
So where are you going to put that 4? Where are you going to put the 2? It's going to be 4 squared. And I hope that's not a big surprise to you. What is it going to equal? 16.
That's it? That's all you do?
And that's all we have to do.
So the answer's already there.
Jeremiah, what's the base right here?
6.
Okay, the base is going to be a 6. And what exponent am I going to raise that to? I'm going to raise it to the 3rd power. And it should equal 216. And somebody just double check that. Why don't you go to your calculator, double check. Is 6 to the 3rd 216?
Why does the next one not have a base?
Yes.
The next one, or we can look on the
All right. And I've already heard the question. About 3 of you are already asking the most natural question possible on this one. And the question is, why is there no base? All right. Okay, 1 is an excellent guess, but it's not correct. 1 is, normally when something's missing, we normally call it a 1, right? This is the few times that it's not, okay? This is a special case that you have to be familiar with, so you need to write this down. This is called a common log, okay? And all common logs are base 10. Base 10. So this is something special that we have to know. It's a common log. So even though we didn't write it here, I could have written it as a base 10, so I would have put a 10 right there. Now, why is it called common? Why do we use common logs? Well, because our number system is a base 10 number system. How many digits are there? 10 digits, 0 through 9. Think about your decimal places. Think about the tenths and the hundredths and the thousands. Those are all multiples of 10, aren't they? Think about your place value, the tens, the hundreds, the thousands, the 10,000s. Those are all multiples of 10s. We live in a base 10 society, so common, this is the most common for us to have, is a common log. All right, so let's rewrite it, please. What would it be? 10 to the 3rd equals 1,000. And double check that, please. Is that true? Of course it is. So again, if I can write a log as an exponent, then I should be able to write an exponent as a log. So let's work backwards. What's the base in this?
Log 8.
Okay, it's log, oops, not capital, log base 8. And I hope you can see that the base of the exponent is an 8. And that is 512 equals, what's the exponent? 3. So it would look like this. Okay? That's all we got to do.
As long as this is all we're doing.
Try the next one. All right? If I'm going to change this to a logarithm, it would be log base 9. That's correct. And I'm raising it to what power? Oh, wait, excuse me. Log base 9 of 27 equals, what's the power? 3 over 2. And take a little time out and see if you can remember if that's true or not. Is 9 to the 3/2 power 27?
Yeah, because we did this yesterday.
Yeah, it is. 9 to the 3/2 is 27. Because you can take the square root of 9, and that gets a 3, and then 3 to the 3rd is 27. So this works out. All right. Look at this last one over here. What kind of log is it?
Negative.
Okay, it's a common log. Do you notice it's common? So it's a common log. So I'm going to say log, but do I write the base? No, I don't want to write the base. Common logs, we don't need to write that. Log of what? 0.001 equals -3. Okay? And you can double check that real quick. Or, you know what? There's another way of writing this. In our class, we're going to be perfectly fine to just stop right there. But in Math 3, where you're going to do most of your logarithms, we're only going to do a little bit this year. When you do most of your logarithms next year in Math 3, you're going to want to change this to a fraction because fractions are much prettier. So what is 0.001 as a fraction? 1 over 1,000 equals -3. And I hope you see why that's better. Because think about it. Is 1,000 10 to the 3rd power? Sure is. So it should make a little bit more sense. Okay? But for what we're doing right now, you can do either one. Questions? All right. That's 80% of your work tonight. 85% probably. Okay?
Oh, it's hard. It's getting hard. It's that BX.
What?
BX.
Oh, my. All right. That's 80% of your work tonight. It's not difficult. Okay?
What are the 15%?
300% of your work tonight. What's the difference? It doesn't matter. But there's one more thing I need you to do. All right? You do have 2 problems that you have to. Are you ready for it?
Yeah, no.
Graph. So have out a piece of graph paper.
Right. You know what I need?
You know what I need?
I need the stuff. I need the stuff.
What?
You go to sleep at like 7 o'clock.
You won't do it.
Oh, we'll do it.
You won't do it.
Actually, I'll still be on the baseball field at 7. I go to sleep on the baseball. Hey, you know what I need?
Yeah,
That would be very bad.
Eating the birds.
Oh, it's out of paper now. I'm sure you'll get you.
Jimmy says.
Why are you so good?
Got you, Roken. I got you, Roken.
All right. Here's what we're going to do. Beginning of class, you came up with a question. We came up with something that we didn't know how to deal with. Okay? We know how to deal with it now. You don't realize it, but you do know how to deal with it. So at the beginning of class, I asked you to find the inverse of y to the bx.
Would you
No, you already know.
I was a betting man. I'd have said it wouldn't have happened. All right. Make sure you understand that the logarithm is the inverse of an exponential. Okay? So think about this. It doesn't come up quite so much this year, but next year in Math 3, when you're trying to solve a division problem, you do the inverse, that's multiplication. When you're trying to solve a square root problem, you do the inverse, that's a square. When you're solving an exponential problem, you'll do a logarithm because it's a new inverse for you. Okay? So here's what I want to do. All right? I want to graph y equals 2 to the x. This is a very specific problem, not a generic one. I want to graph y equals 2 to the x and its inverse. So we're going to do that by graphing it with a table of values. Oh, I see. All right, so we're going to graph this with a table of values. All right, table of values. I think I know what I'm going to use these. -3, -2, -1, 0, 1, 2, 3. And help me fill in the blanks here. Personally, it doesn't really matter where you start. It's honestly easier to start here at 3, but it doesn't matter. Let's fill in these and find out what y values correspond for this exponential. 2 to the third power is what? 8. And 2 to the second power is 4. And 2 to the first is 2. 2 to the 0?
1.
2 to the -1.
-2.
Not correct. It's 1/2. 1/2. Remember, the negative in the exponent makes it into a fraction. Plus, look at your pattern. 8, 4, 2, 1.
2, 4.
All right.
1/4.
1/4
1/8.
and 1/8. So I want you to take a moment and go ahead and graph those on your paper.
They won't have 0, 1 in common.
When we graph the inverse, let's rewrite the inverse. So how would you write the inverse of this? Remember what you do? You switch the x and the y. So this would be x equals 2 to the y. But let's change that to a logarithm form, because I got to have y equals if I'm going to graph it.
Log base 2x equals y.
I agree with you. I'm going to write it the other way, though. I'm going to say y equals log base 2 of x. I just wanted to do y equals first. That's all. So that's good. That's the inverse. Now, let's use a table of values to graph it. Now, that's a good idea. Normally when we do a table of values, don't we plug them in? But what did we find out about inverses about 3 weeks ago?
They're just negative.
Not negative, nope.
Opposite.
What did we do here? Switch the x and the y. What do we do here? Switch the x's and the y's. I don't have to plug these in. All I have to do is take all of these and switch them. So I'm going to do 1/8 -3. And 1/4 -2. And you guys understand. And I want you to go ahead and take a moment to graph those on your own. All right, so as you can tell, when we do get that graphed, they go in opposite directions. Do you remember what is always true about? Yeah, that's right. They always reflect over the line of symmetry. So you can see that that is a reflection over the line of symmetry right there. Okay? And that's the deal with logarithms. It is the inverse of an exponential. So since we're already familiar with exponentials, graphing a logarithm is just the inverse of it. So tonight when we graph logarithms, instead of making a table of values for the logarithms, I want you to make a table of values for the inverse, which is the exponential, and then switch all the values. Okay? So I want you to do your graphs tonight based off of the exponential and then switch them. Now I do want to finish this up by talking about domain and range. So you can tell, give me just a second. So with domain and range, let's look at our domain and range of our exponential. What's the domain of my exponential here? What kind of x values can I choose for this?
Anything greater than
Oh,
0.
I can choose anything. I can choose any number in the world.
I got you.
Because this keeps going up, right?
Yeah,
So my domain is all real numbers. Now what kind of range numbers come out?
greater than 0.
That's right. Only the numbers bigger than 0, because we talked last week, this will never touch 0, will it? All right? Now look at your domain and range for your logarithm function.
This is like a baseball.
Look at the domain and range for your logarithm. What kind of x's do you have for your logarithm? Yeah, only the numbers bigger than 0. Because as you notice, it gets right close to 0, but it never actually touches it, does it? And then the range would be all the y's. It's all real. If you look at this, the y's go forever down, and they will go forever up. So, isn't that interesting? We didn't talk about this a couple weeks ago, but look, the domain and range are opposites, aren't they? And that's true on inverse functions. All right, guys, your assignment's at the bottom.